All right. Well, thanks, and thank you to the organizers for inviting me here. It's been a really fun week. So, I'm a physicist. I'm not a quantum information person. This is kind of a physics-oriented talk, but I'll do my best to try to sort of make it accessible. And the talk is basically about applying quantum information theoretic ideas to analyze some old stuff, old ideas about symmetries in both in condensed matter and in high energy theory. So let me first introduce a notion of chiral symmetry. So chiral symmetry is an important symmetry. It has the topology of U1. And it plays an important role both in condensed matter and in high energy theory. So, one of the most important equations in high energy theory is this one, which describes a Dirac fermion. So these are the Dirac gamma matrices, 4x4 Dirac gamma matrices, and this is the Dirac equation with a mass. So it's known that when the mass is 0. There's an extra symmetry in this equation, which is something called axial symmetry, which I'll explain later. So I'm just sort of giving you an overview right now. So it's a symmetry of massless Dirac fermions. It's an extra symmetry of massless Dirac fermions. But it also emerges in condensed matter. As I already said, there are materials for which the electronic dispersion of that material realizes these kinds of dispersions, these kinds of Weyl fermion dispersions, and that symmetry also plays a role in those materials. And the important thing about this chiral symmetry is the fact that it's not quite a symmetry. So basically, the rough idea is that it is a symmetry at the level of a low energy field theory. Somehow you should think about, when you're talking about quantum field theory, you should think about that quantum field theory Hilbert space as really being a low energy limit of some regularization, some larger Hilbert space, a microscopic regularization. And so the idea behind anomalies is that they're sort of good symmetries of the low energy theory, but there's sort of an obstruction to extending them to be full symmetries of the fully regularized theory. It's kind of hard to give a precise definition just because different people mean different things when they talk about both regularizations and anomalies and everything. But for this talk, the point of view that I want to take is the regularization that I want to consider is what people sometimes call the lattice or the condensed matter regularization, both of which are names that I don't like, but I'll refer to this as the many qubit model. So in other words, I'm going to imagine that all my action takes place in this Hilbert space of the many qubit model. What is the many qubit model? Well, what it sounds like. You have some kind of a lattice in some number of dimensions. You're a two-dimensional lattice, but ultimately be interested in 3 dimensions. And you have some qubits. Okay, maybe they're not necessarily qubits. Maybe they're just some finite dimensional Hilbert spaces. When I'm talking about fermions, they'll actually be graded Hilbert spaces. But all those are sort of details. The important point is that you have this Hilbert space, which is a tensor product or graded tensor product of these local finite dimensional side Hilbert spaces. Somehow that's where all your action takes place. So that's your Hilbert space. The Hamiltonians that will play a role here will be local Hamiltonians. So there'll be sums of local terms. By local, I mean a local term is one that acts on some finite contiguous local region of qubits tensored with the identity elsewhere. By the way, I'm not going to make any. It should be. I already said I'm not a mathematician. It should be very clear these are not mathematically rigorous statements, but you should just think of it as a story. So we have the notion of tensor product Hilbert space. We have the notion of Hamiltonian, and we'll also have a notion of symmetry. So this is what I'll refer to as onsite symmetry. What is a symmetry? In quantum mechanics, a symmetry is implemented by unitary operators. And for what I mean by onsite symmetry, I'll just take those unitaries to be tensor products of unitaries over sites. Okay, so you can imagine like uniform rotation or of a qubit, or a spin flip, or something like that. Yeah.
I think you said already, but I just want to confirm. The fermionic part just means this HI is Z2 graded?
Yeah, exactly. It's like empty and filled states of...
Okay, but then what unitarity means? You just take this whole both as a
Oh, yeah, sorry. Yeah, in that case, what you really want is, maybe group these finite... Take a larger Hilbert space than just the, two-dimensional graded one.
Okay.
So, maybe group a few of them together.
Okay.
And then you can have unitary transformations which rotate between, the even subspace and the odd subspace. Yeah, that's in fact what we'll do. Other questions? Okay, so we'll want to think about all field theories, whatever, as arising from some Hamiltonians of this form. So now, this is kind of it's not a real definition, but it's a good way of thinking about it. So what I'm going to say is that a symmetry is anomalous. As I already said, if it's a symmetry of the low energy Hilbert space of some Hamiltonian, but somehow cannot be extended to be a symmetry of the full Hilbert space in an on-site way. Okay. So some symmetries are anomalous, some symmetries are not anomalous, and among the anomalous symmetries, among the anomalous symmetries, there are symmetries that sort of play a very important role in physics. So, how do anomalous symmetries arise? One important way in which anomalous symmetries arise is that they arise at boundaries of systems in one higher dimension. Okay, so even if you're not a physicist, you should hopefully be familiar with some of these. You can think about the integer quantum Hall effect, with which kind of looks trivial in the bulk of the integer quantum Hall effect. There's a so-called gap, which basically says that there's a gap to excited states. So at low energy, there are no states. So the bulk of the integer quantum Hall state looks trivial. The vacuum outside the state looks trivial. On the edge, you have something called a chiral fermion, which has an anomaly that I'll discuss later. So this is a very general idea within condensed matter physics. There is a whole zoo of so-called symmetry-protected topological phases, which basically exhibit this phenomenon. So the edges of these phases have interesting low-energy excitations, and the symmetry that protects the topological phase ends up having an anomaly when viewed as just a symmetry acting on those boundary excitations, standalone boundary excitations. So that's sort of a condensed matter realization. There's sort of a high energy incarnation of basically the same idea, something called domain wall fermions. So that's the way that these things can arise in physics. That's all well and good, but there's another way to think about anomalous symmetries in the context of this many qubit model, which is, don't add an extra dimension. Stay in the standalone dimension of the theory, but instead relax the on-site assumption. Okay, so that brings us to a notion of quantum circuit. Yeah.
I go back a question. This is like a physics question.
Sure.
So my study of your definition then is, a symmetry is anonymous. It cannot be localized.
Sorry. Symmetry is.
So.
Yeah. It cannot be realized on site.
Yeah. But the thing is, would you consider the many-body cubic model a low-energy physics or high energy? No,
that's high energy. That's the whole theory. That's like your microscopic Hilbert.
Everything's there.
Everything's there, and then, and then maybe some Hamiltonian has some nice field theory limit. Could be, like a, gapless field theory. Could be a TQFT or whatever. But the many qubit model is the original microscopic tensor product Hilbert space.
Most of the time, we don't even care that, right? The theory has too many things we care about.
Yeah, but it's important. So the whole thing about anomalies is that you don't see the obstruction at the level of the low energy. Well, there are ways to see it, but ultimately, a really good way to see the obstruction is that you cannot sort of realize this symmetry in the full UV completion. This is called the UV completion. So as I was saying. There's another way to realize anomalous symmetries, which is, instead of going to boundaries of systems on a higher dimension, instead generalize your notion of local unitaries. So instead of considering on-site unitaries, which are very restricted, it's just like you have to act with some unitary, same unitary in all the sites. Instead, act with a shallow depth circuit of local unitaries. So here by shallow depth, I mean that the depth of the circuit doesn't grow with system size. So implicit in all this is some notion of thermodynamic limit of infinite system size. I want the depth to stay constant. Okay. There's, by the way, also something that I'll sort of refer to. I'll refer to these shallow depth circuits and these Hermitian, these evolutions with local Hermitian operators sort of interchangeably. You should think of this on the right side here as being somehow a continuum version of this shallow depth quantum circuit. This is kind of a discrete thing. You're applying quantum gates which act on some number of qubits at a time. This thing is kind of a continuum version of that. So instead of having a discrete set of gates, you have some kind of a generator, an infinitesimal generator, which could depend on some sort of fictitious time, and you apply that over some time. So the notion of time here is like the notion of the depth of the circuit here. So there's both a discrete and a continuum version of shallow depth circuit, and just by abusing terminology, I'll refer to both these as shallow depth circuits. So by the way, shallow depth circuit of local unitaries. Local is important here. These gates are all act on finitely many qubits in some geometrically local region, and the depth is, as I already said, finite. So these things preserve locality. These unitary operations map local operators to nearby local operators. And they're trivial QCA, but yeah, they're locality preserving operators.
Is the locality depending on tau? I mean, you have the tau at the limit.
Yeah, sorry, this is a bit badly written. I should have just said 0 to 1 integral of some Hermitian operator, which is a sum of local terms with bounded norm.
But is the locality a tau-dependent function? Does it grow with tau? I mean, the tau not in the limit of that one. Yeah?
That one.
Is that growing in tau or not?
No, so k of tau, no, so the k of tau is, there's some locality range that's independent of tau. K of tau is some...
Okay, that's independent.
Yeah, I mean the k itself...
Independent of all taus.
Independent of all taus, yeah. The k itself can depend on tau, but the locality of it does not.
Sure. I mean, you could imagine that locality also grows with time, right?
You could, yeah, absolutely. But in this case, yeah, I'm really trying to make an analog of this. So it's like each layer here, has the same locality. Yeah, thanks.
Just to confirm this picture, so there are two constants here. There's the depth,
yeah,
and also there's a radius.
Yeah, exactly. So you multiply that two to get the Lieb-Robinson microscopic length scale of locality. Good. Okay, so you can do this. Now, is this an interesting thing to do? Well, yeah, it turns out that this is an interesting thing to do. So there's a large class of anomalies that can be accommodated by these shallow depth circuits. So in other words, they cannot be realized in a standalone system in an onsite way, but it turns out that they can be realized with shallow depth circuits. And then there's some other ones that cannot be. So somehow, whether or not an anomalous symmetry can be realized by shallow depth circuits, is a way of classifying anomalous symmetries, a way of, quantum information theoretic way of classifying anomalies. So sort of, in some sense, the less severe ones can be accommodated by shallow depth circuits, and the more severe ones cannot. And we have examples of both. So one class of examples, there are the so-called incohomology SPT states. I think Xia Chen might have mentioned in her talk, and those give rise to anomalies at the boundaries which all can be accommodated by shallow depth circuits, it turns out. But then there's ones that cannot. So it's a natural question about whether chiral symmetry, which is like the first example of an anomalous symmetry coming in high energy theory, can that be represented in a shallow depth circuit or not? So we decided to study this problem. One of the reasons we decided to study this problem is that it was never really conjectured, but it was mentioned that maybe there were some arguments that were given that like maybe chiral symmetry can indeed be represented by a shallow depth circuit. So if you generalize from onsite to shallow depth circuits, then it indeed can represent chiral symmetry. And the answer that we found is that surprisingly no. In fact, chiral symmetry has a very severe type of anomaly, so that its action cannot be represented by shallow depth circuits. And one other thing I should say is that these chiral symmetries, like I said, they're the oldest example of anomalous symmetries. They've been studied forever in field theory. And field theorists also work on the lattice. So these things have been studied on the lattice. But something that I didn't really appreciate until working on this is for the most part, those lattice studies are space-time lattices. They're completely different than this many-qubit model. Somehow it doesn't address the same issues. So somehow, yeah, there is work on extensive work on chiral symmetries in sort of Euclidean space-time lattice context, but it somehow doesn't address this many-body qubit situation properly. Yeah.
So according to your criterion, Hamiltonian lattice theory of the fermions cannot be viewed as shallow depth quantum circuit.
Well, so the statement is that if you take a Hamiltonian, lattice Hamiltonian of fermions, and you make it realize at low energy a Dirac fermion, which there's plenty of examples of, you can write down free fermion Hamiltonians to do that, then the axial symmetry of that Dirac fermion cannot be implemented by a shallow depth circuit in that many-qubit model. Yeah, yeah. So somehow it's a severe type of model. Yeah.
So your qubit model is the space, right?
Yes, it's space. Exactly. Yeah, exactly. Yeah, absolutely. It's a space. That's where the action takes place. All right. So my plan for the rest of the talk, we'll see how much I get through here. I'll review some facts about chiral symmetry. I'll review some facts about situations where you in fact can realize these anomalous symmetries via shallow depth circuits, and then I'll talk about sort of this no-go result that I just mentioned. So, okay, so let's start with something sort of very simple. Topologists in the audience should be able to appreciate this. This is the so-called Nielsen-Ninimiya theorem in 1 + 1 dimensions. So 1 + 1, this notation means one space and one time dimension. One space dimension, sort of the simplest situation that I can think of. And what I've drawn here is a dispersion relation for a free fermion system in one dimension. So on the horizontal axis is the wave vector. So remember, this represents reciprocal space. So k represents wave vectors. Larger values of k correspond to shorter wavelengths. And on the vertical axis, I've drawn energy. So it turns out that any free fermion Hamiltonian in one dimension, free fermion meaning just quadratic particle number conserving Hamiltonian in one dimension, just fermions hopping around on a lattice, corresponds to some band structure like this. This is called a band structure. Okay, it's a single band. Its energy as a function of k. What do we read off from, what kind of information can we read off from this band structure? Well, if we're interested in low energies, and I already mentioned we're going to be interested in low energies, we see that this band structure, the blue band structure line, intersects the E equals zero energy, in precisely 2 points in the thing that I've drawn. At one point, the band structure slopes up and left, and at one point it slopes up and right. So in fact, on the left side, what we have, these excitations are really left-moving excitations. If you think about the many-body system now, where you sort of fill this Dirac sea of negative energy excitations and ask, what does it mean to fill excitations just above this so-called Fermi level? Well, it means that here they're going to be left-moving, and here they're going to be right-moving. It doesn't require much sort of quantum mechanics. If you remember like basic waves, you'll know that the group velocity of dispersion is d omega dk. It's just the slope of this line. So this moves one way, this moves the other way. There's a right mover, there's a left mover. And so it's a very basic fact of topology that the number of left movers is going to be equal to the number of right movers. In this case, 1 = 1. In general, whatever goes up must come down, right? This is a very basic fact in topology. So, this already is something important. It tells us that if I just want to look at a single, let's say, right mover, which is what I'll refer to as a chiral fermion, that single right mover cannot emerge as a low-energy description of a fermion, free fermion Hamiltonian with particle number conservation in 1D, because it would violate this topological fact. This is the Nielsen-Ninimiya theorem in a nutshell in one dimension. Any questions about this picture?
Is the free fermion massless or massive, or doesn't matter?
Well, it doesn't matter. I mean, whether it's massless or massive is a sort of field theory question, right? This is what this band dispersion refers to is you imagine a tight binding model with all sorts of kind of hopping, and this is the dispersion that you get. So when you're talking about massless or massive, what you're thinking about is like some particular dispersion, which might look like this near zero, near zero reciprocal wave vector. So this would correspond to a massless dispersion. This would correspond to a massive dispersion. But those are sort of local features of stations near zero energy, right?
Well, I'm a much naive question because if this is a massless, then
this is massless.
I don't know why it's a right mover.
No, this is massless. Yeah, this is absolutely massless. So these are excitations right near zero energy. These are excitations right near zero energy, and they're sort of asymptotically low energy. You can make arbitrarily low energy excitations that move to the right, arbitrarily low energy ones that move to the left. And the wavelength, once the wavelength gets to be a lattice scale, it makes no sense anymore, and that's sort of the fact that you're only looking at small regions of reciprocal space around some wave vector. Yeah, good. Other questions? Okay, so we have this. This is sort of a first example of an anomalous theory, right? Like a single right mover is anomalous in the sense that the U1 particle number conservation symmetry cannot be realized in a microscopic model in such a way that you only get this at low energies. Now, in fact, in this example, it turns out that these qualifiers that I have here, free fermion, U1 symmetric, particle number conserving, whatever, aren't necessary. So it turns out that here, even if you break particle number conservation, so in other words, allow terms that create or destroy fermions, and even if you sort of move away from the free fermion limit, if you allow non-quadratic interactions, quartics, whatever, it turns out that this is still a true fact. A single chiral fermion just is not, cannot emerge as a low energy description of any fermionic system in one dimension. But you can do something, you can do something a little bit more subtle, which is you can consider the following dispersion. So there's a left mover and a right mover. Okay, maybe they connect up in some way, with larger values of k. So implicit in this is that k is periodic. Minus pi over a is equal to pi over a. This is an S1. But let's suppose that low energies you have a right mover and a left mover. So that's legal, that's allowed, that doesn't violate this Nielsen-Niemiec theorem. I have one thing that goes up, one thing that comes down, that's perfectly legal. But now you can ask a more subtle question about symmetry, which is I can imagine that the right moving excitations carry charge and the left moving excitations are neutral, okay? So that's a symmetry. In this case, the dispersion itself is not chiral, but the symmetry is chiral. This is a U1 chiral symmetry. And so, so in this case, you can ask, is this chiral U1 symmetry, is it anomalous? Can this be realized in a microscopic onsite system, or is there something that prohibits you from doing that? So it turns out that this is anomalous, and the argument for this, I'm just going to sort of quickly say what the argument for this is. I imagine some of you in the audience have seen these kinds of arguments, but the argument, which sort of generalizes to other kinds of symmetries, is basically an argument by contradiction. You basically assume that this thing is not anomalous, and you derive a contradiction from that assumption. So what is assuming that this thing is this chiral U1 symmetry is not anomalous? What does that buy you? Well, if you assume that it's non-anomalous, so in other words, you assume that the U1 symmetry acts on site, one of the things that buys you is that you can gauge the symmetry. So you can couple it to a background U1 gauge field. I don't sort of have time to go into the details of this, so you just have to sort of take my word for it. But when a symmetry is on site, you can always gauge it. You can always couple it to, so here, like the degrees of freedom live on sites, the gauge field lives on links, and you can do this at the level of the lattice in the many qubit model, sort of completely unambiguously. You can couple to an external gauge field. And what that allows you to do, when you have an external gauge field, this is the one-dimensional gauge field. It's a very simple gauge field. There's a vector potential, which you can think of as a one form living on this one-dimensional space, which now I'll imagine the space as boundary conditions. The only thing you can do is basically insert flux through the middle of this, through the whole of this one-dimensional system. So in other words, you can imagine a process that varies in time, and it starts with zero holonomy for this U1 gauge field around this physical system, and ends with a 2 pi holonomy. Okay. So what that process does at the level of this band structure is it turns out to, in a finite system, the allowed wave vectors are quantized to be integer multiples of 2 pi divided by the circumference of the system. So that's only certain values on this x-axis are allowed. And as you insert flux, those just shift. They shift very slowly in one direction, let's say to the right. So what happens is if you have a filled Dirac sea of negative energy fermions like this, and you insert flux, everything kind of moves to the right, and you end up with a situation where the one that was here kind of rode up this escalator and ended up here. Of course, the one that was here, the hole that was here ended up here, so you have a hole here, but that's fine. Let's just focus on the charged excitations. What this flux insertion process gives you is that it basically creates a charge out of nothing. It creates a charge out of nothing. You started with a neutral ground state, and you did something, and you ended up with a charge. And that turns out to be a contradiction. So I didn't give the details of this argument, but this argument implies that it could not have been realizable on site, and hence has an anomaly. And this is sometimes referred to as a Tuft anomaly. Okay. So this is sort of a baby version of what I'll be talking about in 3D. Yeah.
Can I just interpret this as you cannot gauge the U1 symmetry?
Yeah. This is exactly right. Yeah. Yeah. This is, because I was in this argument by contradiction, what I was really doing is trying to gauge it and arriving at a contradiction. Yeah. Mm-hmm. Great. Okay. So now, let me say some words about discrete symmetries. So far, this was sort of everything I was talking about was continuous U1 symmetry. Particle number, the conserved quantum number was an integer, so the corresponding symmetry was U1, was continuous U1. But what you can do is you can imagine breaking that U1 down to a subgroup, like for instance a Z2 subgroup. I apologize for my, I should have really LaTeX this, but I was lazy and I did this instead. But you all know what this means. This is Z2. This is the group with 2 elements. So that you should think of that as a subgroup of U1, right? So basically, whereas the U1 group assigns integer charges to particles or to excitations, many particle excitations, whatever, you can talk about an integer charge. For Z2, you're just thinking about the parity of that, whether it's even or odd. So this is a subgroup of that symmetry group, and you can kind of ask the same questions about whether or not this subgroup is anomalous, and if it's anomalous, can it be accommodated by a shallow depth circuit representation? And here there's kind of a rich story. So it turns out that whether or not this symmetry is anomalous depends on how many right movers and how many left movers you have. So I've drawn a picture here where I have like n right moving modes and n left moving modes, and the right movers are all charged. So those excitations carry Z2 charge, and the left movers are not charged under this symmetry that I'm defining. And I can ask again about, now as a function of n, about whether this Z2 symmetry is anomalous, whether it's not anomalous, can be accommodated by finite depth circuits, etc. So it turns out that when n is equal to 4, when I have 4 charged right movers and 4 neutral left movers, there's no anomaly. That system can emerge as the low energy description of some kind of local fermion Hamiltonian. Now, the interesting thing about it is it cannot emerge as the low energy description of a free fermion Hamiltonian. It turns out that you have to go beyond free fermions, which is kind of what makes this interesting. And there's work on this stuff here and here, which kind of analyzes this problem in the context of conformal field theory and all that. But anyway, this thing is not anomalous. 4 is not anomalous, but smaller numbers are. So moving down, if I have 2 right movers, 2 left movers, the right movers are charged. It turns out that that Z2 symmetry is anomalous, and it can be accommodated by. You can be accommodated, simulated, however you want to think about this, in a UV microscopic completion, many-body qubit completion, by a bosonic shallow depth circuit. So a shallow depth circuit in which all the gates preserve overall fermion parity. They're all fermion parity even. So this is essentially a bosonic kind of anomaly. For one right movers and one left mover, again, it can be accommodated by a shallow depth circuit, but now the gates, you can't get away from having to use fermionic gates. The overall circuit is fermion parity even, but the individual gates, sort of use this fermion thing in an essential way. And then finally, there's n equals 1/2. What is that? Well, something I didn't talk about, but it turns out that the field theory description, when you sort of break U1 particle conservation symmetry, there's a notion of a real free fermion, which is essentially half of this so-called complex free fermion. So you can essentially take half of this picture that I drew before, and that is a valid low energy theory that realizes the Z2 symmetry in a very severely anomalous way where you can't realize the Z2 even by a shallow depth circuit. So there's some nice work by Max Metlitsky and his student Robert Jones that showed this recently. Yeah. Well, 3 is like 2 plus 1. I mean, so by n equals 1, I mean all odd n. By n equals 2, I mean everything that's 2 mod 4. By 4, I mean everything that's multiple.
But then, suppose I do n equals 4 using non-tensor product Hilbert space. Potentially, can you do it or impossible?
N equals 4 or 1/2?
See, 1/2 you have to go to non-tensor product Hilbert space.
Yeah, you have exactly.
I think for n equals 4, you said, it's no anomaly.
No. Yeah, for n equals 4, you can do it in an ordinary tensor product. You need to use interactions. That's a subtle thing. You need to free fermions. There's a Z classification, not a Z8. So the Z to Z8 breaking. Yeah.
I have a question.
Yeah.
So the n1/2, can I also view it by SU2 representations, or is it just complex structure? You see a real and complex structure. But maybe there's also hidden SU2 representation. Is that or not? I mean, you can say it's not, and then I'm also happy.
I don't see an SU2 there, but maybe we can talk after the talk. Yeah. Yeah. Sorry.
You don't see Majorana?
Majorana. Yeah. Majorana is the right word. Majorana. This is a real, Majorana fermion. Yeah, exactly. So Majorana fermion. Thank you. Okay. Okay. So let's see. How much time do I have? 3:20. Okay. So I might skip this. I don't know. I might just say some words about it. So I have a few slides about how, just to sort of, I don't know, motivate this ultimate result, this no-go theorem. I have a few slides about how, in these so-called SPT phases, in cohomology SPT phases, the anomaly can, in fact, the boundary can, in fact, be accommodated by a shallow depth circuit. I'll just say a few words about it, and then, there's questions I can say more, but it's not sort of central to my talk. So let me just say a few words about it. So these people wrote down Hamiltonians. There's a really beautiful story about how you derive these Hamiltonians, their relation to digraph-Witten theory, etc. I'm not going to use any of that. Instead, the only thing that I'm going to use about these SPT phases, these group cohomology SPT phases, is that there's some Hamiltonians in a many-body context, which in some sense are very close to just the trivial decoupled projectors, right? So this sum of pi means a sum of trivial decoupled projectors. That's like the most trivial many-body Hamiltonian you can write. The resulting ground state is the tensor product state. So these are rank 1 projectors, and they project onto a fixed state. So this is like the most trivial Hamiltonian you can write with a minus sign that lowest energy state is whatever satisfies the projectors. So the group cohomology SPTs are basically this, but conjugated by a certain shallow depth circuit, which I'll call the disentangler. And what's special about this shallow depth circuit, first of all, just knowing this form, the fact that it is shallow depth equivalent to just a trivial projector, means that these SPT phases don't have any interesting excitations. They don't support anion excitations in the bulk. They don't support excitations with interesting braiding statistics or anything like that, because they're unitarily equivalent to something super boring that definitely doesn't support that. And you can sort of argue that the presence of anions or topological excitations is preserved under shallow depth circuit. Like if you have a string operator that makes a pair of anions, you can conjugate by a shallow depth circuit and get a string operator in the other theory that makes a pair of anions. So these Hamiltonians are really boring. But the one interesting feature is when you consider them with respect to some kind of an overall symmetry. So the point is that these shallow circuit disentanglers have the property that the overall circuit as an overall operator commutes with the symmetry, but the individual gates that make up the circuit do not all individually commute with the symmetry. Okay, right. So they have these symmetric disentanglers, but those symmetric disentanglers somehow cannot be deformed to a trivial identity operator within the space of symmetric operators. So what that basically allows you to do is it allows you to localize the action of the symmetry to the boundary of the system. So what you basically do is you take this what I called the disentangler V, which I implicitly, even though I drew it with a boundary, I'm implicitly thinking about a system with like periodic boundary conditions or infinite or something. But I can take that and truncate it. So V tilde is a truncated disentangler that only acts in this white region here. And so if I take the truncated disentangler and I act on the ground state of the system with boundary, then I'm kind of disentangling everything inside the bulk. It's like being eaten away and just put into a product state. So I'm sort of isolating a boundary. So this truncated disentangler maps states of the original higher dimensional system into states on the boundary tensor the trivial product state. And if you conjugate by that truncated disentangler, if you conjugate the symmetry action, it also has that property. It maps to some really complicated operator here on the boundary, but it maps to a trivial action in the bulk because the overall disentangler was symmetric. And so these two, these guys, the states here at the boundary and this complicated thing, which now is a locality-preserving unitary, which in fact, in a lot of cases is a circuit, although there are interesting cases in which it's not. That forms this shallow depth circuit representation of the boundary symmetry. That's as much as I want to say about this, unless there's more questions, because it's not really central to my no-go theorem. Okay, no questions, good. So that's just summarizing that. Okay, so now let me talk about, let me go back to talking about the no-go theorem. I already discussed the one-dimensional Nielsen-Ninomiya theorem and chiral fermions in one dimension. What about in 3 dimensions? So this is some of the physically interesting one. We live in a 3-dimensional world. Fermions, we have Dirac fermions in the standard model. Chiral symmetry there is important in understanding that quantum field theory. So okay, so let's see what the analogous situation is that in 3+1 dimensions. So let me just try to do what I did, the simple topological argument, but now try to do it in 3 dimensions. It's a little harder because it's 3 dimensions, but it's still kind of, if you're a topologist, it's still kind of a version of what goes up must come down. Well, not exactly, but there is some topology involved. So, okay, so what is a Weyl fermion? What is a Weyl fermion in 3 dimensions? A Weyl fermion is kind of the 3-dimensional analog of what I call the left mover, a single left mover or single right mover in 1 dimension. So, a single left mover or single right mover in 1 dimension, that was really easy to draw. I only needed one band. I only had that one blue curve, which represented a single band. To talk about Weyl fermions, you need a minimum of 2 bands. So I'm going to imagine that I have 2 bands. So that means, again, I have a reciprocal space, kx, ky, kz. It's a 3-dimensional T3 torus now because, we're living in 3 dimensions. That's my Brillouin zone or reciprocal space. And over each point in the reciprocal space, I'm going to have 2 possible states. Okay, so this is, you can think of these as bands if you're a condensed matter theorist, but I have 2 possible states. And so whereas before I just had 1 possible state, so I just had to specify a single energy function as a function of the Brillouin zone wave vector. Here I have to specify, because I have 2 states, I have to specify a Hamiltonian, a 2x2 Hamiltonian over each point of the Brillouin zone. And so the key distinguishing feature of a Weyl fermion is that the Hamiltonian near the Weyl fermion, which I imagine here sits at kx, ky, kz equals 0, looks like this. Okay, kx sigma x plus ky sigma y plus kz sigma z. You all know what these matrices are: Pauli sigma x, sigma y, sigma z.
Is this SP stands for?
Single particle, I think. Not important. Just LaTeX copied it from some other equation. Okay, so yeah, so just like a single right mover, there's some topological property protecting you from making small deformations that get rid of it. There's also a topological property that prevents you from getting rid of a single isolated Weyl fermion. If you think about adding any kind of perturbation to this, you somehow cannot remove the crossing at zero energy. And one way to see that is to imagine a small ball around kx, ky, kz equals 0. So it's a sphere, it's an S2, a sphere around this point that contains the Weyl fermion. And just imagine the single particle Hamiltonian as defining a map from that sphere into the block sphere associated with these two states over every point in the Brillouin zone. I mean, essentially these two states you think of as a qubit, right? A qubit has a block sphere, and this Hamiltonian turns out to have one positive energy eigenvalue, one negative energy eigenvalue. And so if you just look at the negative energy eigenvalue, that defines some point on the block sphere. And the special thing about this Weyl fermion is that the map from the S2 in reciprocal space that surrounds the Weyl fermion into this block sphere S2 has a winding number, a non-zero winding number of 1. Okay, so that kind of that fact immediately tells you that the number of left-handed Weyl fermions, those with winding number +1, is equal to the number of right-handed Weyls with I mean, obviously you can have ones with higher winding numbers. Let's just imagine there's only +1 and -1. So these winding numbers can be +1 or -1. The sum of all the winding numbers is 0. How do you know that? Well, it's just the sort of trivial topological argument. Like if you imagine surrounding all your Weyl points in the reciprocal space by these little spheres, then the complement of the region the complement of the union of all these balls is some region with no Weyl fermions, no singulars, that has to have winding number 0. So if you sort of pull it through that way, you'll see that you have Weyl number 0. Thanks. Okay, so so far this is exactly like it was in 1D. There's a topological argument that says number of left-handed things is equal to number of right-handed things. But it turns out the three-dimensional world is a little bit different than the one-dimensional world. So in the one-dimensional world, there was just no way to realize a left mover or a right mover by itself. Even if you break particle number conservation symmetry, even if you add interactions, there's just no way to do it. In 3 dimensions, there is. In 3 dimensions, it turns out that you can realize a single left-handed Weyl if you break particle number conservation symmetry. If you break particle number conservation symmetry, this Brillouin zone picture, and hence this argument, breaks. But it's still the world of free fermions, and there is a way to realize just a single-handedness Weyl fermion with free fermions in 3D. And that's using the so-called Majorana mass term. So the idea is you can realize a pair, one left-handed, one right-handed. That's sort of trivial. You can always do that. And then you can gap one of them out by introducing this so-called Majorana mass term. So you can gap out a single Weyl fermion by introducing a Majorana mass term, the so-called Majorana mass term. That's different than in 1D. In 1D, no such thing as a Majorana mass term. I mean, you really can't write anything down that gaps out a left mover. Okay, so I have some stuff here about implications for differences between axial symmetry and chiral symmetry. I'm not going to get into that. It's not that important. But yeah, like I said, the question is now, can this U1 of a single Weyl fermion, if I have a low energy field theory of a single Weyl fermion, like I said, I can in principle realize that with interactions, with breaking the overall particle conservation symmetry. Can I now define some family of shallow depth circuits that makes a U1 which realizes, at its low energy theory, which realizes just the particle number conservation symmetry of that Weyl fermion? And in fact, I'll ask a slightly different question. I'll just imagine that this U1 is generated by some infinitesimal Hermitian generator. So what I'll ask is there a Hermitian charge Q, which is some local operator, some of local terms, local but potentially overlapping terms, which can generate this chiral U1. So I want to note that this is very different from an on-site symmetry. An on-site symmetry, if you think in terms of this Hermitian generator language, an on-site symmetry would be like analogous to a completely decoupled, like if you want to think about that Hermitian generator as some kind of a Hamiltonian, that would be like a completely decoupled Hamiltonian. Here, this is a general local Hermitian charge generator. So this is just like analogous to a general local Hamiltonian. So the question is, can you have this? This is basically the same question, sort of morally speaking, as can you realize this via shallow depth circuits? And so it turns out the answer is no. The argument, we'll see how much of it I can get through. I think I can sort of get to the punchline in the remaining time. But the argument is actually a very nice argument, which if you were at Matt Hastings' talk on Monday, he talked about non-trivial QCA. His argument kind of ultimately boiled down to the fact that the chiral theories in 2D cannot be realized with commuting projectors. In fact, this is the same way we reach a contradiction here. So this is a different problem. It doesn't have anything to do with QCA, but somehow we still leverage that same result from Kitaev. It's kind of nice. So here's sort of the sort of argument. And again, I'm not saying this is a rigorous proof. It's a physics level argument. The argument goes as follows. So imagine adding in this Majorana mass term into my field theory. This Majorana mass term comes with a complex parameter out front. It's some complex number. It has to be non-zero in order to gap out the Weyl fermion. So now let's just imagine I have a single Weyl fermion and I'm going to gap it out. You'll see why. So one thing that I can do is I can introduce a vortex. So a vortex is basically a configuration of delta. So it's delta as a function of space, as a function of three-dimensional space, such that the phase of delta winds by 2 pi when I go around the vortex. Okay, so by doing this, I'm forced to have delta equals 0 in the vortex. That's a topological thing. So there might be gapless excitations in the vortex, but everything outside the vortex has been gapped out. Okay, and so the really cute thing about a single Weyl fermion with this kind of vortex is that the vortex not only might have gapless excitations, it necessarily has gapless excitations. It has a chiral edge state, a C equals 1/2 chiral edge state. This is just a free fermion computation. This is entirely a free fermion Hamiltonian. You can just do the computation. You'll see that a Majorana mass term vortex has this kind of chiral state. And so, okay, so this is again what a chiral state looks like. And just a reminder. So one thing that you know about a chiral state like this is that it can be the boundary of a two-dimensional system. So if you've seen quantum Hall physics, you've seen two-dimensional chiral states, you'll know that this kind of C equals 1/2 chiral edge state is the boundary of a so-called P plus IP superconductor. Some fermionic free fermion Hamiltonian, which breaks U1 down to pairing, which is gapped but realizes at the boundary. So that's a similarity between this Majorana mass term vortex. Thanks. And the P plus IP state, and that's something that we'll actually leverage. So the way we're going to leverage it is as follows. The way that we're going to leverage it is now, remember, we're in the background, we're doing a proof by contradiction. So we have, we're assuming that we can implement this U1 symmetry. By the way, what does U1 symmetry do? U1 symmetry rotates the phase of this delta. That's basically what U1 symmetry does, right? Because this is a charged operator on that U1 symmetry. So applying U1 symmetry globally rotates the phase of this vortex globally. But what we can do, instead of applying the symmetry globally, is we can apply it, but vary it in space. Vary it slowly compared to sort of all length scales that define like this generator, HI. Maybe I should have called this QI. Sorry, this is supposed to be QI. This is the U1 charge generator. It has nothing to do with Hamiltonian. These are supposed to be QI. So what we can do is we can if all these f of i's were 1, this would just be the sort of uniform global generator. But now I can sort of modulate these with a function f that goes from 0 to 2 pi, sort of sufficiently slowly that locally it still looks like it's performing a global U1 rotation insofar as its action on local operators. So this view here you should imagine as being the view the view of this vortex. Sort of cut, like this. So if I perform, if I define this unitary operator that basically, does nothing out here, and begins sort of doing a rotation as I move through, and then does a 2 pi rotation, which again is nothing out here, then it's an operator that basically acts in a region which is like a fattened disk, which bounds this vortex. You should imagine this vortex is coming out of the board and into the board. So in other words, you can insert this vortex by acting on the ground state with this operator that's essentially supported on a disk. So a lot of subtleties associated with this that I don't want to get into, but that's the main message. You can insert this vortex by just acting with the sort of quasi 2D operator that bounds a disk. Now, what does this thing actually do? Well, what I claim is that because this is a quasi 2D operator, it essentially inserts a P plus IP state into the bulk of the system. Now, the bulk of the system is not in a trivial tensor product state, so it takes a little work to make that precise. But the bulk of the system, you can imagine to be in a sort of trivial invertible phase, and so that's sort of shallow depth circuit away from a product state. So anyway, modulo subtleties. What this operator does is it takes and just inserts a P plus IP state, something that looks like a P plus IP state, in fact, in the sense that it has these chiral edge modes, into this 3D bulk. And that turns out to be a contradiction, because essentially you've constructed a unitary, modulo all these subtleties, you've constructed a unitary operator that turns a product state into a P plus IP state. And that's impossible. Why is that impossible? Well, it's impossible because the trivial tensor product state has a stabilizer Hamiltonian. It has a Hamiltonian, a commuting projector Hamiltonian that, is the trivial commuting projector Hamiltonian where you just project onto each side into a trivial state. But then if you had such a unitary that turned that trivial product state into a P plus IP state, into a chiral state, then you would also get a stabilizer Hamiltonian for that chiral state. You get a commuting projector Hamiltonian for that chiral state, for that 2D chiral state, simply by conjugating each term by this unitary. And that's a contradiction. That's a contradiction sort of at the level of physics. That's believed to be impossible, that you cannot have commuting projector parent Hamiltonians for chiral states, for the states which have chiral edge modes that cannot be eliminated. This is discussed in Kitaev's paper, where he gives some arguments for this. Essentially, the idea is that if you did have a commuting projector Hamiltonian, you could sort of truncate the system and expose an edge while staying within commuting projectors, and then you couldn't have a chiral energy current along the edge, simply because that chiral energy current is expressed in terms of commutators of the terms in the Hamiltonian, and if they all vanish, then it's just zero. That's essentially the argument. So that's how we reach our contradiction. Right, so it's a very, very, very long, convoluted sort of sequence of steps, but ultimately you reach this contradiction. Okay.
How did you deduce commuting?
Well, because it's unitarily equivalent to these guys which do commute. So I'm assuming these guys are just acting on disjoint sites, and they're just completely trivial. So this unitary might become complicated, but it's locality preserving, and so some local Hamiltonian for plus AP state. So okay.
There's a length scale. You have to assume the UI does
Yeah,
not.
there's many length scales. So I'm glossing over all sorts of subtleties. There's many different length scales associated with this thing, and like for instance, like how gently you have to do this, spatially varying rotation. You have to the variation of f has to be slow on length scales that are long compared with all microscopic sort of length scales associated with the circuits. But that can all be done. All right. So I'm basically out of time. I'm not going to go into this, but I'm just going to say we have some generalizations to discrete subgroups of U1, where we can, for discrete subgroups, we can't quite prove as strong a result, but we can still prove that certain discrete subgroups of U1 cannot be realized by shallow depth circuits. By the way, it's an open question in that case whether those can be realized by QCA. For U1, U1, because U1 is a connected group and you can continuously deform any sort of generator to the identity, we believe that those cannot be represented as non-trivial QCA, because we believe that non-trivial QCA cannot sort of be homotoped back to the identity. But for discrete groups, it's an open question whether the ones that we found can or cannot be realized by QCA. I think that's a very interesting question. So relevance of QCA is an interesting open question. There's an interesting question about whether we can realize these symmetries, like chiral symmetry, by instead relaxing the tensor product Hilbert space assumption. That's an interesting thing that was done in Mitlitsky and Jones in 1D. I have no idea. And of course, there's really interesting questions about how does any of this relate to like these Euclidean spacetime lattice formulations where, basically there's these Euclidean spacetime lattice formulations in which chiral symmetry can be realized in a very simple way. There's no problem. Somehow, at the level of this many qubit model, it's a very severe anomaly, cannot even be realized by shallow depth circuits. So what, if any, is the relation between that space-time formulation and the many qubit model? I think is an interesting question. But I think I'm going to end there. Thanks for your attention.